Hi, I am Marius Loizu, and today I will present the BuildingNet Challenge held in conjunction with the second workshop on structural and compositional learning on 3D data. First, allow me to introduce my colleagues who have played a vital role in organizing this event. With me on the organizing committee are Melinos Averkiou from Science Center of Excellence and Evangelos Kalogerakis from UMass Amherst. Together, we have worked tirelessly to bring you an exciting and engaging challenge. The objective of the BuildingNet Challenge is to advance the field of part segmentation in the context of 3D buildings, represented either as 3D meshes or point clouds. The challenge aims to promote the development of robust and efficient algorithms that can accurately segment different parts of 3D buildings, such as roofs, walls, doors, windows, and so on. Through the BuildingNet challenge, participants have the opportunity to benchmark their models against a carefully curated dataset and contribute to the advancement of part segmentation techniques in the field of 3D data analysis. Let's now delve into the dataset used for this challenge. BuildingNet is a large dataset of 3D building models with consistently labeled exterior parts. Specifically, it offers 1,849 building models in the form of polygon meshes, which contain 554,000 labeled mesh components corresponding to geometric primitives used by modelers while designing the meshes. Additionally, each model is accompanied by its corresponding point cloud based on the 3D mesh of the building, offering a rich representation of the building structure. So why bother with buildings? Current 3D shape datasets such as ShapeNet and PartNet mostly deal with small-scale objects with relatively simple structure and few number of geometric primitives. For example, the average number of triangle groups corresponding to such primitives is 24 in PartNet, while in BuildingNet it is 26 times larger. This dataset pushes 3D deep learning to large-scale objects with more complex structure. Another motivation is the multitude of applications related to labeling 3D buildings. Structure-aware generative models of 3D urban geometry and texture are becoming increasingly useful in graphics and virtual worlds. Labeled parts can also facilitate style-related analysis of buildings. Finally, synthetic building datasets may also be useful to train or pre-train 3D urban recognition pipelines. Creating this dataset was not easy. Inexperienced human workers can easily mislabel domain-specific parts such as domes or buttresses. On the other hand, hiring experts such as architects to label thousands of buildings would be time-consuming and costly. Another complication which affects human and machine annotation is that building meshes are non-watertight with tens of thousands of polygons. It is hard to label polygons one by one or draw segmentation boundaries on them. An observation that can help us here is that building meshes often have useful metadata, such as groups of polygons corresponding to geometric primitives used during modeling, such as the ones you see on the right. These groups can simplify human annotation and may improve machine annotation. One last challenge is that building parts often vary a lot in terms of size, even within the same building, such as the domes you see here. They can also vary a lot in terms of geometry and texture across models. I will now discuss the human annotation pipeline used for creating the BuildingNet dataset. First, we mined several thousand of 3D models from the 3D warehouse repository. Various quality checks were performed to remove models with too few polygons, groups, and no texture. We corrected geometry problems, including reorienting the normals and removing the generated polygons from the meshes. We also removed the interiors through raycasting, since our goal was to label building exteriors. We then performed a small-scale study involving architects to label a small set of our buildings and find the most common labels they use. 31 such labels were identified as visualized here, creating our target label set. Our next step was to find human workers capable of performing this task. After worker training and evaluation, we picked only reliable ones from Mechanical Turk. Finally, annotations were gathered by using an annotation interface. Our dataset evaluation phases offer the training, validation, and test split in a proportion 80, 10, and 10%. The right column shows the total number of labeled components, or in other words, polygon groups per split. I also want to highlight the average number of labeled groups per model in each split of BuildingNet. Across the dataset, we observe an average of 635 annotated components per building shape. This demonstrates the richness and complexity of the dataset, offering challenging benchmarks for 3D part segmentation of large-scale objects with intricate structures. Now, let's discuss the two main evaluation phases offering the BuildingNet challenge. In the first phase, called BuildingNet-Mesh, algorithms can access the mesh data, including subgroups and texture. In this aspect, they can take advantage of any pre-existing mesh structure common in 3D building models. The second evaluation phase, BuildingNet-Points, is designed for large-scale point-based processing algorithms that must deal with unstructured point cloud data without access to mesh structure or subgroups. For each mesh, 100,000 points with Poisson disk sampling are obtained to achieve a near uniform sampling. For each point cloud, point normals and RGB texture information that originate from triangles are also available. We also offer two dev phases where participants can submit their predictions on the validation split in order to familiarize with the BuildingNet dataset and the online submission platform. The winning participant team of each phase is picked based on their performance on the test split. Now, let's dive into the evaluation protocol used for the BuildingNet dataset. The evaluation protocol is designed to objectively assess the performance of the participant models in part segmentation of 3D buildings. Since most part classes are commonly encountered across different building categories, all evaluated methods should be trained across all building categories. Methods must also effectively address the challenge of part class imbalance present in the BuildingNet dataset. The dataset exhibits variations in the distribution of different part classes, with some classes being more prevalent than others. Therefore, participants' methods need to be robust and adaptive to handle this class imbalance scenario. For evaluation in the point cloud phase, the metrics of mean part IoU and shape IoU are used, along with per point classification accuracy. For the mesh phase, a variation of the previous evaluation metrics is applied on triangles, where the contribution of each triangle is weighted by its area. The winning team for each phase is selected based on its part IoU performance. To facilitate the BuildingNet challenge, we leverage the power of EvalAI, an open source platform designed for evaluating and comparing machine learning and artificial intelligence algorithms at scale. EvalAI provided us with a robust infrastructure to host the challenge and streamline the evaluation process. Using EvalAI, we were able to create multiple evaluation phases and dataset splits, accommodating the diverse requirements of the challenge. This flexibility allowed participants to train and fine-tune their model using the training and validation splits, while keeping the test split concealed until the end of the challenge. Let's now discuss the baseline methods employed for the two evaluation phases of the BuildingNet challenge. The baseline methods provide participants with a starting point and a performance reference for their models. For the BuildingNet-Points phase, we tested a classic unit architecture that utilizes residual blocks. This network was implemented using the Minkowski engine, an auto-differentiation library for sparse tensors. For the mesh phase, we tested various baselines. One simple baseline is to first sample points on the mesh, then use Minkowski-net to extract per point descriptors, and finally aggregate the descriptors for each triangle. Aggregation is performed by using min pooling on the descriptors of points belonging to each triangle to extract per triangle descriptors. Then we employ an MLP and classification layer to label each triangle on the mesh. We transfer point descriptors to triangles using the architecture that we used in the point phase, yet the performance remains low. Another baseline is to transfer descriptors from points to groups of triangles, which correspond to larger geometric primitives in the mesh. Here we find all points belonging to each triangle group, then performing pooling of their descriptors to extract a descriptor per group used for classification. Since the aggregation of point descriptors happens over primitives larger than triangles, the labeling performance is improved. Now let's take a look at some statistics and key highlights from this competition. The BuildingNet Challenge took place from March 15 to May 24, providing ample time for participants to showcase their expertise in 3D part segmentation. We received participation from 10 teams, each bringing their unique perspectives and innovative approaches to the challenge. In the BuildingNet-Points evaluation phase, we received a total of 5 valid submissions from the participating teams. These submissions showcase the participants' approaches and algorithms for part segmentations of 3D building models represented as point clouds. And now, the moment we've all been waiting for, the announcement of the winner of the BuildingNet Challenge for the BuildingNet-Points evaluation phase. It gives me a great pleasure to announce that the winner is Shicheng Xu, who secured the first position with a part IoU performance of 31.3%. Shicheng's submission demonstrated a slight improvement over the baseline, showcasing his exceptional efforts and expertise in 3D part segmentation. Now let's dive deeper into the outstanding performance of our winner. Shicheng will present his submitted method and will highlight the improvements he made over the baseline model.
Hi, this is Shichen Luke Xu. I'm presenting my submission to the BuildingNet Challenge and my project multitask 3D building understanding with multi-model pre-training at Stanford CS231N course. I'm currently a machine learning engineer at Google Geo team and also a SCPD student at Stanford. First, let's talk about my submission to this challenge. I trained a PointNext XL model on BuildingNet-Points track for 3D building part segmentation. The PointNext model improved over PointNet++ model in 3 areas: data computation, optimization technique, and the model scaling. On the model architecture, it adds an inverse residual MLP layer, which adds a residual connection to allow the model to train deeper, and it uses separable MLP, which adds MLP layers after the reduction stage. This is similar to MobileNet to reduce the model size. Lastly, the output channel of second MLP layer can be expanded for model scaling. Comparing to the baseline LinkNet, my PointNext XL model applies the same random rotation before voxelization and use the same voxel size 0.01. I use a smaller sample size, 40,000, and applied all the data computation from Pointnext. I loop the dataset 12 times per epoch and only train the model for 100 epoch. For the loss, I use the same weighted cross-entropy loss. The test result of my Pointnext Excel model marginally beats MinkNet, but significantly improved over PointNet++ by over 100%. In this project, I explored a new task from the BuildingNet dataset, which is called 3D building type classification. It basically produces a class label for the entire building object, such as castle, cathedral, and church. The chart below shows the class distribution of building types, and we can see it's super imbalanced. I propose a multitask model architecture to tackle both building part segmentation task and building type classification task. I explored multiple various learning strategies for this problem, including training from scratch, transfer learning from a different data set, multi-model pre-training using ULIP framework, and combine that with multitask learning. ULIP is a multi-modal learning framework for text, image, and point cloud. For BuildingNet, I generated 64 text prompts, 16 multi-view images and depth map, and pre-process point cloud model for each 3D building to form the triplet to train with ULIP. I pre-trained Pointnext model with ULIP from scratch for 100 epochs, and for comparison, I also loaded the baseline MinkNet model and trained it on ULIP for 50 epochs. The result on the right shows that a good segmentation backbone can also help train a good ULIP classification model. Finally, here is the experiment result on both classification and segmentation tasks. We can see that multitask learning with ULIP pre-training consistently achieves top performance on both tasks. You can find more details in this course poster. And that concludes my presentation. Thank you for listening. If you're interested, the paper will be released on arXiv. Thank you.
Before we conclude, we would like to thank Shicheng for his presentation and contribution to the BuildingNet Challenge. We would also like to express our sincere appreciation to all the teams who took part in this competition. As we are near the end of our presentation, let's summarize the key aspects of the BuildingNet Challenge. The competition focused on the task of 3D part segmentation of buildings, aiming to advance the state-of-the-art in this field. The BuildingNet dataset that was utilized for the purposes of this challenge provides a rich and diverse collection of building models with annotated exterior parts. We hope that this competition has sparked new ideas and inspired further advancements in 3D part segmentation of complex structures such as buildings. For those interested in delving deeper into the BuildingNet dataset and exploring the challenges and opportunities in 3D part segmentation, we invite you to visit our project and challenge websites. Thank you for your time and active participation.